So for the attendance, you can use the Padlet. I have created the separate groups for this group A and group F and group E. So you can just put your name there and as well as your student ID. Thank you. So today practical, Bismillahirrahmanirrahim, Assalamu alaikum and good morning. So I hope my voice is okay, right? You can see me also, right? Video is also okay.
Yes.
Thank you very much. Thank you. So this practical is related to the stereochemistry, right? So stereochemistry of organic compounds, right? So stereochemistry and application of the drug molecule with the help of the models, right? So I have the model with me. So inshallah, we will go uh, from the simple example as well as the some of the selective problems which has been given in the your lab report, right? So not all so selectively, but I will give you the clear concept of the stereochemistry and what type of the problems uh, given in the lab report, right? So first of all, in your lab report, so I can share the lab report. So can you see this PDF?
Yes.
Right. So we will go one by one, right? So I hope you don't have this model set, right? I don't think, right? So this is how it is. I will try my best to show you each and everything, right? So this is how this model boxes look like. This one, right? So this have some, just like you can see this model, right? Can you see? Can you see the model and all, right? Students, yes.
Yes,
Yeah,
doctor.
so please cooperate me because I don't know whether you can able to see or not, right? So because it's a uh, synchronized and then as well as the symbiotic relationship between you and this me, right? So the box contains some this atom, for example. You can see this one. This one is the black one is the carbon, right? This one carbon, and this one is the hydrogen, right? And this one is the hydrogens, right? So this is the model of, you can see this is the model of the cyclohexane, right? So cyclohexane is, you can see the number of the carbon should be 6, right? So you 1, 2, 3, 4, 5, 6, right? And then it has hydrogen, right? So this one is, you can see this one is the hydrogen, right? This one is the hydrogen. So I have make the models of this some of the cyclohexane as well as the simple butane. You can see this one, the butane model, right? So use this one carbon, this one carbon, this one carbon 1, carbon 2, carbon 3, and carbon 4, and then this one is the hydrogens, right? So in the in and butane you have the CH3. So in this one you can see the CH3, this is the 3 hydrogens, right? 1, 2, and 3 hydrogens, and the 3, so methyl group, and this CH2, this is methylene, This is also CH2 methylene, and this is the methyl group, right? So this is the cyclohexane, right? So this is the no, and this n butane, right? Not n butane, and this one is the cyclohexane. You can see. So this model is right. Can you see these models?
Yes.
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 So
Yes.
so I have shown you the this how the model boxes look like, and I have created some of the models, right? So it is very easy, no problem, right? So because it is uh, this is how the this carbon is look like. You can see this one, right? So this is how the carbon is look like, right? So and then after this the hydrogens, so this is the hydrogen. You can see this one, right? This is how the hydrogen, and this is how this carbon, right? So carbon have four this sp3 hybridized, right? Four substituent, right? It have the valency 4, right? And this is on carbon, right? This one, and then this one is the hydrogen, right? So just I have created for example, you can see that this one is the uh, one molecule which contains different groups, right? So this is the carbon, and these are the substituent, right? So this is how it's look like, right? This one is the middle one is the carbon, and then this one is these one are the four atoms, right? So this one you can see this one, right? So you can see, so it's very easy to construct this model. So you can see how, right? So this is how it's look like, right? This one, right? So this is the bond, right? Single bond, right? Single bond. And then this one is the atom, right? So how you can see is this one we have to just um, create the bond like this, and then this one how, right? This is how I have created the this model, right? Like, so this is how, so all the models, for example, this is the cyclohexane, all model has been constructed so the same way, right? So like this, so these are all the single bond, right? This is the sp single bond, all single bond in cyclohexane, all single bond, right? And then these are the hydrogens. So that's this is how you can see in the series here in this practical construct simple alkane and cyclo alkane in 3D model, right? So 3D model. So I have created for you the cyclohexane, and this is the simple alkane, which is the um, and butane, right? So far, no problem.
No
No,
problem.
doctor.
Yeah, so can, if you have any problem, just let me know if that, right? So these are the 3D models, right? These are the 3D models. But from these models, very easy to understand the stereochemistry, right? Because stereochemistry is the like a spatial chemistry, right? The molecule chemistry in the space, right? How the molecule are look like in the space, right? 3D model. So you can see this one 3D model of the molecules, right? If you construct this molecule, or if you draw this molecule on a paper, that will be the 2D. For example, the line structure, or this Newman projection, or the seahorse, or the Fisher projection, right? So the this so you have to draw some of the Newman projections, as well as the sawhorse, as well as the Fisher projection of the molecule. So you can see this one, this one is simple the 2D structure, or you can see the when you construct the molecule on a paper like this, right? So and then after this we have to see in this practical, right? So first objective is the we have to we have to construct the model, which is the 3D model or the 2D model. 2D is about this Newman, the sawhorse, as well as the Fisher projection. And then after this, understanding whether the molecule, for example, we can go the three different topics in the stereochemistry, which is the enantiomers and diisomers and the meso compound, right? So what are enantiomers, right? Enantiomers are the molecules which are the two molecules which are mirror image to each other, right? But non superimposable, right? They are they are non superimposed mirror images. They are called enantiomers. And the second thing is the distereoisomer. You can, the distereo means two stereo center. So what are the stereo center, right? So so you can see this compound, right? So this is the carbon, right? And then this one is, these are the molecule, these are the atoms, 1 2 3 and 4. And you can see this one is the blue, this one is the green one, this one is the blue one, and this one is the red one, and this is the hydrogen, right? So this is hydrogen, and for example, this one is a bromine, this is the chlorine, and this is fluorine, right? So all the atoms which is attached to this carbon, right? They are different, right? They are non-identical, right? So this carbon is called the chiral carbon or asymmetric carbon, chiral carbon. So this is the stereogenic center, the stereo center, right? So chiral carbon is the carbon which have all four unsymmetrical group or the different groups, right? For example, this one is this one is the bromine, this one is the fluorine, this is the chlorine, and this is the hydrogen, right? Like these, right? All four, right? Like this, right? So all four different atoms. So this one is the carbon is stereogenic center, right? So for example, one more example I can give you, this one. uh, this one, right? This model is, you can see this model, this model have two similar groups, right? Two similar groups, which is the hydrogen, and this is, for example, fluorine. This is fluorine, and this is the bromine, right? So you can see two similar atom, like this one and this one, and this one is the fluorine, and the this one is the bromine, right? So these are, so this carbon have two symmetrical groups. So this is carbon is a non-stereogenic center or achiral center or achiral carbon. So carbon, if the carbon have all the four different group in this one, so they are the chiral carbon, right? Chiral carbon, the unsymmetrical groups on the attached with the carbon, right? And this one is the two symmetrical groups, right? Which is attached to the carbon, like this, right? Two symmetrical group, identical group, and two groups are a different group. But these two similar groups makes these two similar atom make this carbon achiral, right? Not chiral. So chirality means all four atom attached to the carbon, they are unsymmetrical or different groups. So here you have clear the concept of chiral carbon.
Yes.
Thank you very much. Right, so here you can see, and so this one is so enantiomers, right? So enantiomers are the two molecule. For example, I can give you the example of the enantiomers, right? um, so for example, right, so these are the groups, right? This one, right? So this one is the these are the two compounds, right? Two compounds. So for example, I want to make the, so you can see like this. So this one, right? So here this one, so if let's say we want to make this mirror image of this compound, right? So how the mirror image will be, you can see this one is a mirror image, you can see this one, right? So these are the mirror image. You can see this one and this one green, and then this one is the red one. So these molecules are the mirror image to each other, right? Mirror image, right? Can you see?
Yes.
Yeah, thank you. So this
Yeah.
one is the mirror image. These are the mirror images, right? So when we the when, so these are the compound with the mirror image. But when we superimpose these one, right, like this, right? So you can see I have superimposed like this. So this green one with the white one, and white one with the green one, and then this one, right? So but these are non-symmetric, non-superimposable mirror images. So they are called the enantiomers. So these are the enantiomers are the compound which are mirror image to each other but non-superimposable mirror image. They are not able to superimpose, right? They are not able to superimpose. So these are called the enantiomers. So right. So what are the distereomers? Distereo means two stereo center. So there's not necessary that the two that the any molecule which has two chiral carbon or any molecule which has the chiral carbon, they should be they can be they can be the enantiomer. They can be that identical molecules, two identical molecule, if they have the plane of symmetry. If they have the plane of symmetry, they are the identical molecule, right? So distereomers, but what? How you can define the distereomers? Distereomers are the molecules, right, which are not mirror image, right? If the molecules having the chiral centers, right, and they are not mirror image to each other, right? They are not mirror image to each other, right? So they are not identical, right? They are non-identical mirror images, right? That means they are not mirror images, right? So they are called the distereoisomers. And meso compounds, the compound which have plane of symmetry, right? The compound which have the plane of symmetry. For example, you can see cyclohexane, sorry, this one n-butane, right? Is right. So n-butane, if you cut or if you put the mirror in between this one, right? They are identical. Both part is identical, right? They are identical means they are similar when the plane they have the plane of symmetry, right? If they have the plane of symmetry, right, they are called the meso compounds. They are called the meso compounds. So these are how you can see the enantiomers, distereomers, and meso chemical structure. And optical activity. So what is the optical activity? Optical activity is the, for example, this one compound which I show you previously. This is the chiral carbon. If the molecule is chiral carbon and they are mirror image to each other, non-superimposable mirror image, so they are enantiomers, right? So they can rotate the plane of polarized light. So for example, so that for this one we have, for in order to check the optical activity, we use the polarimetry, one apparatus or one instrument which is used to see the whether the molecule have the chirality or not, right? So that instrument is called this optical act or this the polarimetry, right? So usually the concept of the polarimetry is, for so in the polarimetry there is the polarized light, right? So for example, this is the polarized light, for example, right? This is the polarized light. When it strike to the chiral carbon or chirality in a molecule, right? So it will rotate clockwise or anti-clockwise, right? So only it rotates either clockwise or anti-clockwise once they have there is any chirality in a molecule, right? So it because of this chirality, the plane of polarized light can rotate clockwise or can rotate anti-clockwise. That's how we can see whether the molecule has the chirality or not through the polarimetry. And then after this, understanding this uh, CIP model, which is the R and S. These are the absolute configuration of a molecule, right? So, so here you have to should have the clear concept between this configuration as well as the conformation. The configuration is the two molecule, for example, which I've shown you, the two molecule. This one, right? The two molecule, these two molecules are these two molecules are not identical. They are similar. They are mirror image to each other, but non superimposable mirror images, right? So meaning that they have different stereochemistry. They have the different configuration, right? In order to change the configuration, we have to break the bond, right? In order to convert the R in the one enantiomer into the second one, we have to break the bond. This is called the configuration of a molecule, right? In order to change the configuration, we have to break the bond and change one molecule into another one, right? So here if there is a two enantiomers, so those both enantiomers should have the different configuration, right? So for example, if you have learned in your lecture also, right? So for example, this one is the carbon. We want to check the what is the absolute configuration of this molecule, right? So we have to apply the CIP rule, right? So what generally the CIP rule tells us, right? So it usually tell us the priority level, right? So we have to give the priority to the molecule, right? So what I can previously what I can say that this one is the bromine, this one is the chlorine, and this one is the fluorine, right? Just you can assume this one is the fluorine, small one, and this one is the hydrogen, right? So then the priority level, what you have the in this model, you have to give in the priority. The biggest atom this molecule is this bromine, and then after this chlorine, and then this fluorine, right? And then the last one is this hydrogen. Listen, this hydrogen, right? So we have to give the priority. This for the priority level 1, and then this one is the 2, and this one is the 3, and this one is the 4, right? So what we have, we can how from the 3D model, how you can uh, define the configuration of the molecule. You can hold from your hand like this and move this hydrogen at the back. At the back means if from my side it is at the back, but from your side it is front, right? So we move this hydrogen at the back like this, right? For yourself, right? I have. So this one is the hydrogen at the back, and then this one is the bromine, this one is the chlorine, and this one is the fluorine, right? And then now priority level, we have to assign the stereochemistry of this carbon, right? Whether R or S. So how we can go from this 1, 2, and 3. 1, 2, and 3. This is how the anti-clockwise, right? If the configuration is just like anti-clockwise, right? So this one will be the S, right? If for example this molecule, which is the mirror image to each other, right? This one, right? This one is another molecule. 1, 2, and 3, right? This one is clockwise, right? So this one is the R, and this one is the S. You can see how this one is R and S, right? So you can see the priority level 1, 2, and 3, right? One is clockwise and other one is anti-clockwise. Clockwise is R and anti-clockwise is S. So far, okay?
Okay, sir.
Okay.
Okay, thank you. Right? So this is how you have to assign the stereochemistry, right? And then after this, we will apply this concept on a one drug molecule, whether in that drug molecule, whether there is any stereogenic center or not. how many chiral carbons in that, and how we can assign the stereochemistry of that molecule, right? So this is the objective of this practical. In this I have explained you the 3D model, and then enantiomers, diisomers, if the molecule is identical, right? So they have, means for example, the molecule, for one molecule have different 2D structures, for example, Newman projection, Sawhorse, and Fischer projection, right? So one molecule have different conformation. For example, the second concept is about the conformation, right? For example, you can see this one is cyclohexane. You can see the chair conformation of cyclohexane. You can see like this, and one is the carbon at the bottom, one carbon is at the top, and this one is the two other carbon. So this is the chair conformation of cyclohexane. Chair conformation of cyclohexane. You can see chair conformation of cyclohexane like this. So you can see like this, right? Can you see?
Yeah.
Yes. So this is how, right? So so this cyclohexane have different conformation. For example, you can move this one model like this. So this one, it will automatically move like this. So you can see this one, it automatically. So this one you can see, this one is the boat conformation, and then after this it will be have the second conformation like this. So this one is the another this board conformation of this molecule, right? So this one, so one molecule have different conformation, means many conformation. For example, the best example is, you if any person is dancing, right? So meaning, so it has different conformation, right? It has, but same person dance, it has different movement of their hands and movement of the this leg. So the one, so molecule is same, but a molecule have is same, but it has different conformation. So meaning that the two molecule have, if the two molecule have different configuration, it means they are different molecule. If one molecule has same, if the one molecule have if one molecule have different conformation, means different there's a molecule have different position, but the molecules are same. For example, in case of the cyclohexane, they are the different conformation in the chair conformation, boat conformation, twist boat, and all. So they are the different conformation of the same molecule. They are identical molecule. And then the example which we have seen, the molecule which the, the molecule which have the molecule which have the same the look, you can see the molecule, right? So the molecule which is the mirror image to each other. So they are mirror image to each other, but non superimposable. They are different, they have different configuration. One is R and other one is S. So meaning that they are different molecule, they have different configuration, different R and S configuration. So far is okay?
Okay.
Right. So this is how the concept you have to apply here, right? So the first model is the 2-chlorobutane, 2-chlorobutane, right? So I have shown you the uh, so this is I show you this cyclo. This one is the normal this N butane, right? Carbon number one, carbon number two, carbon number three, carbon number four, right? So the first is prepare the model of the 2-chlorobutane. 2-chlorobutane means carbon number one and carbon number two, right? So I have to taken out the one this one hydrogen, and replace with this hydrogen with the chlorine, right? This is how this one is the 2-chlorobutane. This is the 2-chlorobutane. This is the methyl group. This is the chloric, this chloride, and this is the hydrogen CH2 and CH3. Like this, you have seen there in your line structure, right? So, or you can see like this also. This is how the in the line structure, right? This one is how it is look like, right? Means this is the methyl group, this is the chloride group, and then after this hydrogen CH2, and then after this one is the CH3. Understand? So how you have to prepare the or construct the model of these 2-chlorobutane. So where is the stereogenic center in this one? Is this you can see where the carbon which has the stereo center or the this chiral carbon, this one, right? This one, this carbon has four different group. This one is CH3, right? This one is Cl, and this one is hydrogen, and this one is CH2 and CH3. So this has one stereogenic center. This have the one stereogenic center. Is it okay? Can you able to see this one? This carbon,
Yeah.
right? Right?
Yes.
Right. So that's how you have to go, right? So and then for example, we want to just I am going through this how you have to have the first stereogenic carbon, and then just you have to assign the stereochemistry of this carbon, for example, right? So you have to assign the stereochemistry that you have to be have the same rule of this one, right? CIP rule, right? So in the CIP rule is you have to give the priority, right? So in this molecule, this one is the chloride, this one is the hydrogen, this one is the methyl group, and this one is CH2CH3. So I hold this the chloride, and then I move this one back. Hydrogen is at the back. What will be the front? This one is the chloride, and this one is CH2, CH3, and this one is CH3. And hydrogen, the lowest priority level, the atom, which can be anything but having the lowest priority or low molecular weight compound, atom, right? Low atomic number, atomic weight the atom, right? So this one is the chloride, and this one is the hydrogen at the back, and this CH2 and CH3, and this one is CH3, right? So you can see as how you have to assign the stereochemistry. Well, this one and this one is 2, and then this one is 3, right? So how you have to move 1, 2, and 3 clockwise. Understand? 1, 2, and 3. This one is how you have to go clockwise, right? So if so this one is the what is the absolute configuration of this carbon is, please? Yeah, what will be the what is the
S.
how it would be as? It will be clockwise. Clockwise will be R, and anti-clockwise will be S, right? So you can see this one is chloride, and then this one is CH2, CH3, right? And then this one is the methyl. So how we have to move? Clockwise, right? Understand? Clockwise, right? From your perspective, you can see how we can move is clockwise, like this one. From here, fit the second priority, and then third one. This one is when you move the clockwise, it will be the it is the R, and then if anti-clockwise, it will be the S, right? So so one I can show you. You can see this one. Can you able to see this slide?
Yes.
Yes. So this is how the clear concept of this one. The model I already shown you how this model can be, right, like this. So now this model is like this. This is 2-chlorobutane, right? 2-chlorobutane, right? So blue is the methyl group, right? So this one is the you can see how the first you can see how you can make the model, which I already told you how to make the model, right? And then our second thing is from the model you have to construct the you have to assign the stereochemistry of the stereogenic center, right? So in this one, in this model, you can see that this one is the carbon, and this one is the chloride, and this one is the methyl group, right? Yeah, this one. So red one is the chloride group, and then this one is this one is the biggest one, which is the CH3 CH2 CH3, right? So from here you have to move from 1, 2 and 3. 3 is the methyl group, and then this one carbon, right? This one is CH. This one is the stereogenic center, and then this one is the carbon with CH2, right? And CH3, this one. So number 1, number 2 and 3. From here, this one is the clockwise. And you can see in this one, the second one is here you have the priority level 1, two different opposite stereochemistry of this mirror image 1, 2 and 3, and then this one is the anti-clockwise, right? So this is how you have to assign the stereochemistry of the molecule. So it's very easy to if you assign in the plain paper, right? So in the plain paper is just you have you should have you for example this one for example this one is your uh, carbon, right? And then this one is your chloride, and this one is your CH3, CH2, and CH3, right? So how in the paper you can see, right? Just move line means line structure, right? For example, you have, I can show you. You can see this one, this is the line, this is the line, and this one is the weights, right? So line means it is up at the back, right? Line is means at the back, this one is at the front, right? So if you make the model of this molecule, this one, so this one is at the line, right? And then this one is come in front, right, with my side, right? This one, right? This is the side view, and this is at the top is the chloride, right? So hydrogen I move, this is at the back, which is in the line, right? So I'm telling you how to assign the stereochemistry on a paper. So 1, you have 2, and you have 3. So you have the anti-clockwise. You have the anti-clockwise movement, right? You have to move from 1, 2, and 3. And this or the what will be the stereochemistry of this stereogenic center is S, right? How you have to map, you can assign the stereochemistry of this molecule. So this one is stereogenic center, and the what is the you have to assign. The first question is about the you have to complete the drawing as well as, and then you have to assign you have to assign the stereochemistry of this stereogenic center. So this is I have shown you this one example, which is the S isomer or S 2-chlorobutane, right? As 2-chlorobutane. If we go to the second one, the similar model for the another molecule, which is the R configuration. So how you can go with the R? How you can go with the R? The question arises, right? So if you so see how I'm making this R, convert this S into R. You can see, as I told you in the absolute configuration, we have to break the bond. If we want to change one molecule into another, we have to break the bond, right? So I am just breaking the bond, CH3 like this, and this one is CH2, right? CH2, CH3. So like this, so I have to construct the this like this, and then like this. Like this. This is how we have to break the bond, right? We have to break the bond. Then you can see hydrogen is at the back, hydrogen is at the back, and then you have this one, you have from your side, right? So I just move this one like this, hydrogen at the back, right? This one is 1, this one is 2, and this one is 3. How we move from here to here, right? Which is the clockwise, which is the clockwise. This one chloride, CH2, CH3, and CH3. This one is clockwise. That's how I convert this S into R. So this is the another example, isomer of this. One is the S2-chlorobutane. The second one is R2-chlorobutane. That's how you have to assign the make the two models of the this CIP, about this two model of the 2-chloro butane, like this. So what I have seen, tell you the example, this one. So that's how you have this one. You can see this is the Newman projection. So how you have to form the Newman projection, right? Newman projection is on the paper, right? So very easy, right? You can see how the Newman projection can be, right? Like this. This one is the R, and this one is also R, right? So this one you can see, this one is the carbon which is at the dot carbon, right? So for example, this one, this carbon, this one carbon is at the dot carbon, right? You have um, like this, right? So this one is the two hydrogens with this carbon dot, and then this one is CH3. And at the back, what is at the back is chloride, CH3 and hydrogen, chloride, CH3 and hydrogen, like this, like this. So I'm just telling you how to construct the Newman projection, right? In the Newman projection, the this circle is this one. You can see this one circle is at the back, and this one is the carbon which is come in front of us. Come in front of us. So this one is, for example, this one is carbon. This one is the carbon, right? So this one is CH3, right? And then this one is two hydrogen. The CH3 and two hydrogen, right? That's how Newman projection is. You can see this carbon, right? This one, and this carbon, and then this one is CH2, and this one is CH3. And what will be the at the back, which you can see these lines are coming chloride. This one is the chloride, and then this one is the hydrogen, and this one is the CH3. That's how. So you can see the how the model is look like. So CH3, this is you can see like this, like this. You can see this is the carbon, which is this carbon, this one, right? This one, and this one is 2CH2, right? The two hydrogens, and this one is the methyl group, right? So this is already complete. This one dot, and then like this. And what at the back is the CH3, Cl, and hydrogen. So like this at the back, right? So you have at the back, so like this. So at the back, you have the chloride group and the methyl group and the hydrogen. That's how you have to construct the 3D or this Newman projection. So in the Newman projection, what you have to see, just you can take the one carbon, one hydrogen, one carbon which is come in front of us, right? And then after this, you can have the group which is attached to the carbon. You can draw like this, CH3, H and hydrogen. So like for example, you have the two and this chlorobutane, right? So this is the carbon, this is the hydrogen, and this one is the hydrogen, CH2 and CH3. And at the back, you have the carbon with the hydrogen and methyl group and chloride group. right? So this is the this is how you have to assign the stereochemistry, or this you have to make the Newman projection of these 2-chlorobutane, right? And then how to assign the stereochemistry of this stereo center is the same way. You move the carbon, you move the lowest priority level, which is the hydrogen at the back, hydrogen at the back, right? So this is the chloride, right? This is the chloride you have, and this is the CH2 CH3, right? The second group, right? And this one is the third group, right? This is 1, 2, and 3. Move like this: 1, 2, and 3. This is the R. And then in this one here, you can have the chloride group. And then after this, you have CH2 and CH3, and then methyl is here, right? You cannot move like this. How? Because CH2 is here, right? This one is chloride. This one is the chloride, right? And this one is CH2, CH3, and methyl group. So like you have like this, right? This is the anti-clockwise or counter-clockwise, which this one will be the S. That's how you have to show that's how you can show the both isomer of 2-chlorobutane, which is R 2-chlorobutane and S 2-chlorobutane. So far, any problem? Students, so far any problem?
No.
No. Okay, thank you. So that's how you have to make the two isomer to both enantiomer. You can see apply the priority number of each of the 4 group and name each drawing as R and S. So you have to mention R and S according to the CIP rule, which I told you how one is should be the isomer, one should be the R, and other should be the S. And then after this you can see the same, because we have the same examples, right? 2-chlorobutane, we have to see we have already seen that these two molecules, the one is R and other one is the S. So R and S both are mirror image, non superimposable mirror image. So can I show you non superimposable mirror image of this molecule? Then it will be very easy for you. This one is the second model of this n-butane. So I'm just going to make the this one is, we have already assigned this one. You can see on the base of the priority level. This one is chloride. This is CH2 CH3, and this one is methyl. This one is R. This one is R. 1, 2, and 3 clockwise R, right? So now we have to move this convert this R into S, right? So Can you able to see? Just hold on. Just focus on this, what I am showing, what I am uh, projecting, like this. Understand? So this one is hydrogen, hydrogen. This one is chloride and chloride. This one is the methyls and the CH2, CH3. Can you see this one, right? So these are how this model is. These are, so one is R and other one is S, right? So they are, though they are mirror image, non superimposable mirror image. So you can, if I put like this, if I put like this, you can see chloride is at the hydrogen, chloride at the hydrogen, and then this one is methyl with the CH2OH and like this. So non superimposable mirror image they have, right? Non superimposable mirror image, right? So if let's say you want to see what both enantiomers have the different configuration, so you have to assign this one, for example, this one like this. I hold this one here, this one, right? So I hold like this, I hold like this, right? I hold like this, right? So this one you can see chloride, and then this one is the chloride and this CH2OH, and this one is the methyl, like this, clockwise. This one is 1, 2, and 3. This one is R. And then you can see this one, right? Oh, what happened? Hello?
Hello, doctor.
Yeah, yeah. Can you see my picture is okay or it's already still, huh?
Okay.
Okay, okay, because at my place is so in this one you can see this one is the chloride group, this one is hydrogen at the back, CH3 and CH2. This one is the chloride and then CH2, CH3, and then, right? So this is the anti counterclockwise. This one is the S and this one is the R. So both are the enantiomers, right? One is R and another one is S enantiomer. So far, okay? Students, so far, okay?
Okay.
So I already told you how to make the Newman projection. For example, one more example of this one Newman projection, the same molecule, right? So if you want to make the Newman projection, you can very easy, right? So the Newman projection is on the page, right? So this one you can see this one is the carbon, right, which is the dotted one, and the round is at the back. You have the round, and that you have the dot in between is the dot carbon is which is in front of you, right? So this is the dot carbon, this one, and then this one is hydrogen, right? This is the hydrogen, this is the methyl, and then after this you have the one side is the chloride, and other one is the CH3, and bottom is the hydrogen, like this. So this is the Newman projection. This is how the Newman projection. Methyl group, hydrogen, hydrogen, and at the back one chloride and CH3 and hydrogen. This is how you have to form the Newman projection of the molecule, right? So this is how the very from the Newman projection also very easy you can assign the stereochemistry of the molecule. This is the you have the chloride, right? This one is the chloride group. This one is the chloride group, right? This is the highest priority molecule atom, chloride. This is CH2, CH3, and this one is the methyl. So you have the S configuration counterclockwise, which is the S, right? So you can see this one steady 3 mod model. So we have seen this 3D model, how the 3D model of this and this 2 chlorobutane looks like this, right? So for example, the chloride is at the back. About you can see this one. You can see the how the Newman projection of this one. So the carbon, the stereogenic carbon is in front. For example, we can say we can look like this. This you can see this one, this one is the carbon. This one is carbon, and this one is the chloride, and this one is the hydrogen, and this one is the methyl group. At the back is CH2 and CH3 at the back, right? So you have the Newman projection. You can see how the Newman projection look like of this compound. This chloride is at the bottom. Chloride is at the bottom, right? Chloride is at the bottom, and then after this you have this hydrogen. Hydrogen is like this. You have the hydrogen like this. This one hydrogen, and then methyl is this one. Methyl is this one. This one is hydrogen. This one is the methyl group. This one is the chloride, right? And at the back you have two hydrogens. You have two hydrogens at the back, right? Two hydrogens at the back. You can see this is at the pointed at the bottom, right? Like this, right? Like this, like this, like this. So this one is the two hydrogen and methyl at the top, like this. Understand? So how this is how you have to say you can able to make the 3D model of this Newman projection. Is it okay? Right? So one more time I can just uh, uh, explain you. This one is the chloride. This one, see, yeah, this one is the chloride which is at the bottom. This one, right? So like this you can see the chloride is at the bottom, right? Chloride is at the bottom, right? And then this one is the hydrogen, which is this one, and then methyl, which is this one. So like this you can see, like this. So this is how you can see the this chloride and the hydrogen and the methyl group. And at the back you have these two hydrogens, and this one is the methyl group, like this. This is how the Newman projection of this molecule. So this one is the Sawhorse projection, right? So Sawhorse projection is chloride is at the bottom, right? Chloride is at the bottom, right? And then this one is come at front like this. So you have this one is hydrogen, one is the methyl group. So you have the methyl group, which is this one is the chloride, and this one is the methyl group, which is in the wedge, and hydrogen is at the back. Hydrogen is at the back. So this is how you can convert this Newman projection into the this Sawhorse one. And then at the back, which is the two hydrogens and the methyl group. You can see the methyl group, this one, and one is hydrogen in front of this coming pointed at you, and then one is at the back, right? This is how we can study the 3D model of the two normal two butane in the Sawhorse, like this. And then this one is also same, but you can see this one is the same molecule. But these all are the same molecule which have different pictures or different projection, right? So meaning that this is a project. For example, this one is, we have assigned the stereochemistry of this one, right? This is chloride, and this one is the CH2 CH3, and this one is the methyl 1 2 3 R configuration. So this one is all the molecule have the R configuration, but and then this one, these are the different projection. So this molecule have different projection in the Newman projection and the Sawhorse, and the other this one is also the Sawhorse projection. So these are the same molecule which with the same projection having the different conformation. If the so meaning that the one molecule have different picture or different conformation, they have same molecule, because here the bond is not break. So if the bond is not break, right, so meaning that molecule have different conformation. You can see how the molecule can move like this, molecule can move like this, right? So these are the different conformation of the molecule. They have the same molecule which with the different conformation, right? The same molecule with a different conformation, right? So like this, so meaning that one molecule have different conformation. You can see that molecule in Newman projection or Sawhorse or Fischer projection. These are so these are the projection, different projections or different conformation of the same molecule. Understand? Students
Yes,
understand?
sir.
Right.
Yes.
So like this, so this is how the same the complete the Newman projection of second molecule, which is the this the another this stereoisomer, right? For example, the you have to study with the R, and with you have to study with the S also. So for example, like this one is the S1, this one is the S, right? So this one is S, right? So how this one is chloride, this one is CH2 CH3, this CH2 CH3, sorry, and methyl. 1, 2, and 3, they are counterclockwise. They are counterclockwise. So meaning that they have stereochemistry is S. So remember, counterclockwise movement of molecule is a configuration will be the S. So how in the paper you have to make like this. So for example, you move this hydrogen at the back, means line structure, and then one metal is projected, right? These at front, and then this one is at the side, and chloride at the top, and 1, 2, and 3, this one is anti-clockwise. That's how you have to. So this one you have to see steady with the R as well as the S, right? So the Newman projection in case of the air, in case of the this one, you can see the Newman projection of this molecule. How the Newman projection of this molecule will be? This one you can see the this one, yes, you have the this methyl group, you have the methyl group like this. So this one carbon is we have chosen for the another configuration, right? But of this molecule you have this this one methyl group, right? This one is you have the methyl group, right? And then after this one is the hydrogen, right? And this one is also hydrogen like this. So you can see this one is methyl group, this one is hydrogen, this one is methyl group, this one is hydrogen, and this one is also hydrogen like this, right? So hydrogen, right? And at the back you have the chloride group, you have the chloride group at the back, right? And then one is the methyl group, and one is the hydrogen group like this. So this is how. So this is a staggered conformation of the molecule, right? If, like for example, the if chloride is near to the this methyl group, there will be the eclipse conformation, right? So there are the two type of the conformation of the same molecule. One is eclipse. So they can form like this. So you can see if the biggest group two big group is on the same plane, they are the eclipse conformation. So if we move like this, so they will be converted into the staggered conformation, meaning the different one molecule have different conformation, but they are the same molecule. They are the same molecule. So like this, so you have to do with the model B and C. You have to I already told you the answer also, right? But you have to be uh, um, um, construct not you, because as you have the don't have the model, so you can construct all these in the 2D projection, right? Like this one is the complete Newman projection of the D. For example, you have D like this Newman projection we have seen, like, right? So these are different conformation of the same molecule. Fischer projection is simple line one. You can just say straightforward, you have this line, and then this hydrogen and hydrogen CH2, hydrogen and hydrogen and CH3. These are the Fischer projection of this molecule. So they are the same molecule having different same molecule having different conformation. So do the Newman and Fischer projection represent the different conformation of the same molecule? Of course, the answer is already given yes, right? Right. So this is how you have to go like this, yes or no, like this. Now we come to the second example, which is 2,3-dichlorobutane. 2,3 dichloromethane. So for example, we have R. Just I am giving, I already told you of the basics of, already tell you the basics of the all the stereochemistry, right? So make, and here these are, we have the molecule is 2 R2 chlorobutane, right? R2 chlorobutane, we can see how the R2 chlorobutane is, can be, which one is, you can see this one is a hydrogen at the back, which is pointed at you. And then after the CH2, O, CH2, CH3, and this methyl. This one is 1, 2, and 3, clockwise R, right? So here the question is 2 model of R. 2 model of R means 2 model of R, right? So I can, so this one is how, this is the one model, right? So how the second model will be. So these are both are the, both these both are the these both models are the R models. So to make two models of the R butane, right? So now in this one we have to replace one on one model we replace the hydrogen Ha, and the second model we have to replace the hydrogen Hb with the chloride molecule, right? With the chloride atom, right? So for example, you have this one is Ha and this one is Hb. So replace this one with the chloride like this with the chloride, right? Like this with the chloride. So this so for example, you have 2, 3, right? So this one is 1, this one is 2, and this one is 3. Understand? So 1, 2, and 3. So 1 I replace this one with the chloride. So like this. So yeah, I have replaced one hydrogen with the chloride, right? Ha, and this one is Ha, and this one is Hb. Understand? So in the second molecule, which is the same, which one is the same as this one, like this one. So in this molecule, these are the both are the similar molecules, right? They are similar molecules, right? In first one I replace this one is Ha and this one is Hb. In the first one I replace Ha with the chloride, right? In second one Hb, this one is Hb, right? So I am replacing this one with the Hb with the chloride like this. Sorry, it's fall down, huh? These are the look like a ball, huh? So you can see in this one you this one this in this one I replace one hydrogen Ha with the chloride, right? And then is here at the bottom you can see this one at the bottom, which is Hb. I replace this Hb with the chloride. So these are the two model, which is all both are come from R2 chlorobutane. So one is so both are 2,3 dichlorobutane, right? 2,3 dichloromethane, 2,3 dichlorobutane. CH3, 1, 2, 3, and 4. 2,3 dichlorobutane, right? So this one also, the 2,3 dichlorobutane, this one also the same, right? In this, so in the bold model, we have replaced the different hydrogen and the substitute both the hydrogen with the chloride, right? So like this. So of course you can see here we have replaced the Ha, right? Uh, and then here we replace the Hb in this one, right? In this one you can see like this. So this one, both molecule, in one molecule we have replaced Ha with the chloride, and the second molecule we have replaced the Hb with the chloride. So both hydrogen is at the different position, of course, right? So are these one or two modules are same or different? Yes.
Different.
Yes, they are different models, because in what one we have replaced the Ha, and the second one we have replaced the Hb. How? You can see in the model very clearly it is stated that you hydrogen, this one chloride and up top, and this one is the chloride at the one chloride at the top and one is at the bottom, like this, like this, right? Like this. In the second one, you can see this one chloride at the top, and this is Ha. Replace Ha with the chloride and replace Hb with the chloride. Are these models are same? No, right? They are the different models. They are the different, right? Different models, and they are actually so just you can apply. I'm not telling you all the answers, right? So if they are not identical, whether they are stereoisomer or not, so you have to answer, are they enantiomers or not? So enantiomers, I already told you definitions. If the molecules are mirror image to each other, right? And known, so these mirror image are the known superimposable, so they are enantiomers, right? So if they are not mirror image, then they will be distereomers. Understand? So either the are the enantiomer can be yes or no. If enantiomer is yes, then diisomers will be no. Right? If the molecule is enantiomer, it will be not a diisomer, right? Because they are mirror image. In enantiomers, they are not mirror image or non identical. Understand?
Yes.
Yes,
Yeah.
thank you.
Yeah.
Yes.
So like this, you have to answer this one like this. Will replace. So if the molecule is different like this, so you have to replace and see. Name the model. Of course, we can name the model, right? For example, you can see. Just I am telling you the name. That's how to name the model, right? So you can in your paper also you can make the model, and then you can see. So there are two stereogenic center, right? One now previously in 2 butane there is one chiral carbon, right? In this one there's two chiral carbon, right? There's a two stereogenic center, right? Right. So you can see this one carbon, hydrogen, chloride, CH3, and then this one, right? So this one is stereogenic center, right? Number one. Number two, this carbon, hydrogen, chloride, methyl, and this one molecule, right? So there are two chiral center, stereogenic center. There are two stereogenic center in the molecule. So now I'm going to give the name of this molecule, right? So give the name of this molecule. So you can see this one is the chloride. So first I will give you the name of the number two. What is the name? What is the stereochemistry of number two carbon, and what will be the stereochemistry of number three? First, number two. So we have to apply the CIP, right? So move this hydrogen at the back, right? At the back means it's from my side is at the back, and from your side is in front, right? So I move this one, I'll move this one, for example, at move toward you. This hydrogen is at the back, right? And chloride here, and then this one is the methyl, and then this one is also the bigger group, right? One, two, and three, like this, counterclockwise, like this counterclockwise. Understand? And then so this one is S. This one is 2S. 2S. And then this one is, you can see this one, the second one is like so second one we have to move this hydrogen at the back, at the back. Then so at the back like this, so I can move from here. This is at the back, chloride at this one, chloride rotate. And then after this one is 1, 2 and 3. This is R, like this. So 2S 3R like this. So this is how you have to so it means these are having the different positions of this chloride group. Means one is R, one is S. Maybe in that other molecule it will be S and R. So R, R and S, S, they are an enantiomer, or S, R, or and the R and S, they are an enantiomer, right? So meaning that if the one molecule have RR configuration, so the mirror image will be the S and S. If the one enantiomer say having the R and S, the other one will be the S and R. If the enantiomers have S and R, the other one will be the R and S. Understand? So these are the enantiomers. What are the diisomers of these compounds can be? But dienantiomeric pair will be R, R and S and R. R, R or and the R and S. So they are not, they are non-superimposable. They are not mirror images. R, R and S, S, they are an enantiomer. R, R and S and R, they are diisomer. And S and S and the R and S, they are diisomers. And then you can have the S and S and R and S, they are diisomers. And S and S, R and S, so they are mirror image to non-superimposable mirror images. They are exactly opposite. S and S and opposite is R and R. They are enantiomers, right? If there's S and S and R and S, R and S, so they are not opposite, of course. They are, meaning they have the, they are known, they are not mirror images. They are di-zero isomers. Understand the concept?
Yes, doctor.
Thank you
Yes.
very much. So the same thing you have to apply for the S2 chlorobutane, right? So S2 chlorobutane, you have to replace the this Ha with the chloride and Hb with the chloride, and then you have to see. So these are the Newman projection, right? So don't be confused that how. So I already told you that for example, this one, this pointed carbon, which is you can see this one because I already convert this one. So this one is, I can you can see this one CH3. This one is the chloride group and this one is hydrogen, right? Like this you can see. You can see this one is methyl, this one is chloride, this one is hydrogen. At the back you have at the back you have the chloride group, which is oriented like this, chloride group, and this one is the hydrogen and this one is CH3 like this. So you have V like this is CH3, hydrogen and chloride. Understand? So this is the Newman projection. This is the Newman projection, the 3D model of the Newman projection of this molecule, model 3. Model 3, right? So like this. So this is how. So this one always, this carbon is this one, right? And then this hydrogen is you have this one Hb, and then this one is methyl at the top, and at the side there is a chloride. Understand? And at the back, which is the round at the back, and then this one is which is at the back, right? This one is hydrogen. You have this one is hydrogen. This one is the hydrogen, and then this one is the chloride at the bottom, and then this one is the CH3, which is this one. This one CH3, hydrogen, and chloride. This is how you can easily make the just imagine the 3D model, and then you can make the this Newman projection of the compound. So very easy to give the name of this molecule, the configuration of molecule with the help of the Newman projection, right? Move this hydrogen at the back. Move this hydrogen at the back, right? You have the chloride group, you have bigger group, and then this one you can move like this R configuration. This is how you can make, you can assign the stereochemistry of the chiral carbon with the help of Newman projection, like this. And for this one, second one, you can see this one is at the back, right? For example, like this is at the back, so I can move this chloride top priority here. This one is at the back, like this, at the back. This one is the chloride, and then this methyl. This one is, you can see 1, 2 and 3. This will be clockwise, R and R, like this, right? So like this you have to make do all with the, because all with the R and R also and S, because these models are the S1, right? So the R and R will be the same, right? So you have to assign the stereochemistry of these, or both model 3 and model 4. Of course, if you replace the different hydrogen, of course it will be a different molecule, right? Because we in the first model we replace the HA with the chloride, and the second one we replace the HB with the chloride. So they are not a similar molecule. They are different molecules. They are the different isomers. So like this is same. If S and S will be the enantiomer will be the R and R, right? Or R and R enantiomer will be the S and S. So what will be the diisomers? What will be the diisomers? S and S, R and S, or S and S, S and R. They are the diisomers. They are the distereoisomers. They are not mirror image. So you have to like this answer the same. Model 3, you have to give R and S configuration and S and R. I already told you how to make the S and R, because there are two stereo center. So one will be the S, another will be the R. Or one will be the S, and other will be the S. S or R or R, or R and S, or S or R, like this. So they have the different, absolute configuration, like this. So like this, you have to label that whether the compound 1 and compound 3 identical enantiomers and diisomers on the base of your previous answers, right? On the base of your previous answers, one R, and I already give you the examples. S and S will be the opposite one, will be the R and R. They are enantiomers, right? And S will be the if other will be the S and S and S and S and S. They are identical molecule. S and S and R, they are enantiomers. R and R and S and S, they are enantiomers. R and S and R, they are diisomers. And S and R will be the R and R, they are diisomer. So just you have to compare with the previous answer that whether they have the same exact opposite stereochemistry, they are enantiomers. If they are not identical, they are not mirror image, then they will be the diisomers. Understand? Understand?
Yes.
Yeah. So like this, so up now we come to the concept of the this meso structure. Meso, what is the meso compound? Meso structures, I told you that meso compound are the molecule which have the plane of symmetry. So maybe I can give you the example. Chirality, I already explained you. They are the best example of the chirality is our hand, right? These are our hands. They are enantiomers. They are non-superimposable mirror images. So they are the chiral molecule. They are the chiral. So like this, so non-superimposable mirror images like this, so they are non-identical, right? You can have the mirror images, so it's the same, which I have shown you in the model, hydroxyl, hydroxyl, methyl, methyl, and hydrogen and CH3OH, right? So they are non-superimposable mirror images like this. So these are how the enantiomers can be. They are non-superimposable mirror images, right? So mirror images. So you can see in this molecule, right? In this molecule, the CH3 and CH3 and this is hydroxyl group and hydrogen. They are mirror image, but when you put into this one, they will be superimposed. If the molecule is, they are mirror image, but they are superimposed, they are identical molecule. They are not enantiomers. You have to keep in mind that enantiomers are the mirror image, non-superimposable mirror image, right? If the superimposable mirror image, they are not enantiomers, they are the same identical compounds like this. So now here you can concept of planar symmetry comes, right? So if let's say for example this molecule CH3 and hydrogen and chloride, if you put the plane here, they are symmetrical molecule. They are symmetrical molecule. Symmetrical. Both sides are symmetrical. This so meaning that this molecule have plane of symmetry, right? So for example, in here they have the plane symmetry, CH3, chloride is half here, and hydrogen half here and half here. They say they are achiral because this molecule have the plane of symmetry. But this molecule you can see, if you this molecule is the stereogenic center, all four different um substituents, right? So meaning if you have the, if put the mirror here, so they are not have the plane of symmetry, right? They are not plane of symmetry. They are not identical on both sides. You can see CH2, CH3, and then chloride and hydrogen. They are non-symmetrical, so they are chiral. So this is how if the molecule have plane of symmetry, they are called, they are, these molecules are the meso compounds. Meso compounds are the compound which have the plane of symmetry, right? So this is how I already told you that how to move, right? For example, this one is the Newman projection, right? So you have this hydrogen, right, and hydroxyl group CH2, CH3, and CH3. So how you assign the priority level? This one hydroxyl, of course, these are the top priority, hydroxyl group, chloride, bromide. It's right. So number one, this hydroxyl group, number one. Number two is this, after that one, this, the second largest is CH2, CH3. Third largest is the CH3, and fourth is like this. So you have the model like this. And then after this, what you can see is from the Newman projection, from here to here, from A, B, and C, right? Like this, you have the A, B, and C, like in Newman projection. In 3D model, you have to move this carbon, hydrogen at the back, and then you can see now A, B, and C. This one, so this one moving to the clockwise, they will be the butanol, or in our example, we have seen the 2-chlorobutane, like this. So this is how chlorobromide, chloride, fluoride, number one, number two, number three, right? Lowest priority level will be the fluoride at the back. So here is number one, A. Of course, chloride is larger than the bromide. A, B, and C. Like this anti-clockwise, they will be the S configuration. So how you convert this one into the Newman projection is, this is carbon which is appointed like this, right? Top is the bromide, and then after this is chloride and the iodide. This is chloride, iodide, and fluoride is at the back, right? So then you have from here to here, opposite, this one is counterclockwise movement, that will be the S configuration. In the plane of symmetry, right, in the plane of symmetry, you can see this molecule is the disubstituted cyclohexane, right? So you can have if you put the plane mirror here, so this molecule have plane of symmetry. This molecule is plane symmetry, you can see, right? If you put the plane, the methyl here, hydrogen here, and hydrogen here. So this one is having the plane of symmetry here. This molecule is also have the plane, cis and trans both have the same plane of symmetry, right? They are opposite. If you put the plane, they are symmetrical in nature. So this is the molecule having the plane of symmetry. These compound molecules are called the meso compounds, right? If the molecule have the plane of symmetry, they are called the meso compounds, right? So compound can be the meso compounds, right? Plane of symmetry, right? Can be the identical and enantiomers and isomers. So far, okay.
Okay.
Now we come to this example of the substituted cyclopentane. Substituted cyclopentane is um, so you can see how I'm just construct the models, right? So I'm now constructing the cyclopentane. This carbon number 1, carbon number 2, carbon number 3, carbon number 4. Now I replace this hydrogen with the carbon. So this is how you can see this one. So now you can see. Sorry, what happened to my picture? So like this, you can see. This is cyclopentane. This is cyclopentane, one carbon, like this, like this. One carbon, second carbon, third carbon, fourth carbon, and fifth carbon, right? So this is cyclo. This is cyclopentane, right? So cyclopentane having the 5 carbons, right? 1, 2, 3, 4, and 5 carbon. CH2, 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 and CH2. Is it okay? Can you able to see?
Yes.
Yes.
Yes. So now I am replacing according to your this now I'm this so this cyclopentane, and now I'm replacing the one hydrogen with the chloride, right? So you can see this how this one is one straight line, this one, and this one. Now this one I'm talking about this one how. So you can have I just replacing one hydrogen with the chloride, one hydrogen with the chloride, like this. So I replace one hydrogen with the chloride, like this. So this is so this one is the chlorocyclopentane. This is the chlorocyclopentane, right? So how this is how you have to make the chlorocyclopentane, right? So one more. So here also you have to do the same thing. This you have to play with the two. You have the two models, right? Two models of this cyclopentane, chlorocyclopentane. In one model, you have to replace this one. So we have replaced here. You can see the one hydrogen Ha replaced by the chloride, and second one Hb replaced by the chloride, right? So for example, you can select one Ha, and this one is Hb. You replace this one with the chloride like this, so yeah, this is the dye substituted chloro. This one is the dye substituted dichloro cyclopentane, right? Dye substituted cyclopentane, right? Or 1,2 dichloro cyclopentane, right? So now you are this. So this one molecule you have to see where. So this one molecule can have this one is identical or the non-identical. So here the concept can come, which is the cis and trans, right? Cis and trans. How the cis will be, the cis molecule are the molecule which have the all the groups are on a same plane. For example, here is difference is chloride, right? Here, so this one you can see this chloride is on the plane on the same plane. If they are on the same plane, they are called the cis. So if I replace this hydrogen like this. So this is a chloride and this is chloride, right? They are opposite, and this is perpendicular, opposite, anti position, right? So they are the trans, right? So if the molecule, so if let's say for example, I replace in the two molecule one I replace Ha with the this one, right? Ha with the chloride. In second one Hb with the chloride. So in one molecule the chloride is on the top, both chloride on the top. The second one, and when I replace Hb with the chloride is at the bottom, which is the trans. So cis and trans, though both molecules, of course, they are the different molecule. Understand? So they are not identical. Of course, they are cis and trans, right? So cis and trans. So now you have to assign the stereochemistry of this one. Of course, you can easily assign the same. You have to assign the stereochemistry by the same way which I have told you in the previous. Hydrogen is at the back. Hydrogen is at the back. This is the chloride, and this part of the molecule is second priority because of the chloride. So this one is the carbon, chloride, and this part of the molecule 1, 2. You have 1, 2, and then this one. This one is the third one. Carbon 1. This one chloride. This one is CH chloride, and this one is CH2. 1, 2, and 3. This one is R, right? And then for the other one, you can have like this. This one is the hydrogen. This one is the chloride, and this one is CH2, and this one is CHCl. So number 1, number 2, and number 3. You have to rotate, and this one is anti-clockwise. This one will be the S. That's how you have to go like this, whether these molecules are molecule 6, what R and S, and molecule uh, uh, 18, and this molecule 6 will be the R and S, or like this. The molecule 5 will be the name the R and S, right? So you have to name like the one. This you have to name like this: 1S 2R dichlorocyclopentane, or 1R 2S dicyclopentane. That's how you have to give assign the absolute configuration of the stereogenic center. So you have to answer like this, just like the same as you write the IUPAC name: 1S2R dichloropentane, 1R32S dichlorocyclopentane. Like this, you have to answer like this, right? So if molecule the molecule is meso, if so, indicate the plane of symmetry. So in the cis one, right? the cis one, right? Well, in the cis molecule, I can show you the plane of symmetry. Just I'm showing you the plane of symmetry, how the plane of symmetry can be, right? So, like this, you can see both chloride is on the top. If you put the plane, cut the molecule, chloride, plane of symmetry. Understand? If you put the mirror here, the molecule is same, chloride, and the upper chloride, hydrogen, CH2, and then hydrogen and hydrogen. They have the plane of symmetry. This molecule is have the plane of symmetry like this, because both have the chloride group on the same. Understand?
Yes.
Thank you very
Yes.
much. Right. So this is how you have to assign which molecule is plane of symmetry. If the molecule is plane of symmetry, both molecules have the plane of symmetry, right? They are the meso compounds, right? Like this. Now we come to this cyclohexane one, right? So far what we have discussed here is the simple example 2-chlorobutane. Then we have construct a model of 2-chlorobutane, and then after that we have seen the RNS configuration, and then assign the RS configuration, and then after this we have substituted when one hydrogen HA with the chloride and make the another stereo center, right? And then in the same thing we have done with the second isomer, S isomer, and then you have to assign the stereochemistry of both carbon, right? In previous one, which have the 2-chloro, only one stereogenic center. When we replace the hydrogen with the chloride, then 2 stereo center. You have to assign the stereochemistry of both carbon, right? Then we have seen the example of the cyclopentane, right? Chlorocyclopentane. So in this chlorocyclopentane, we have also did the same thing. We replace the one hydrogen of HA with the chloride, and the second hydrogen HB with the chloride. And then you have to assign whether if the molecule have the plane of symmetry, they are identical molecule. If the molecule if don't have that plane of symmetry, they can be if they are mirror images, they are non-superimposable, they are enantiomers. If they are not identical, means they are not mirror images, they are the diisoisomers. Like this, you have to answer whether they are diisoisomers or enantiomers, like this. Now we come to the example, which is the cyclohexane example. So I show you the cyclohexane molecule. This one is cyclohexane. Can you able to see cyclohexane? This one is, right, cyclohexane. Can you see?
Yes.
Right, this cyclohexane. So now that's how we construct the model of cyclohexane, right? Then this is same as the chiral. If there's a chiral mirror images mod, right? So if they're identical, means if molecule is identical, it means they can superimposable, right? I giving you the example of methyl, CH2, and chloride, right? So hydrogen, chloride, and the hydroxyl group or chloride group. If the molecule have the plane of symmetry, they are these molecules are identical molecule. So now you can have the cyclo. This one is the cyclohexane. Now I am you can see, now I am making the model of this 1,4-dichlorocyclohexane, right? So this one is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So like this. So I am replacing one with the this. So you can see this one. This one is both conformation of this molecule, right? So I'm replacing this. So like this. So you can see in the chair conformation, uh, all the hydrogens which is on the top, right? So these hydrogens, these are axial, right? This one is axial and this one is equatorial. This one is axial and this one is equatorial. This one, you can see this one is the equatorial, it is toward the equator, and this one is axial. All 6 hydrogen you have on the top, they are axial, and with the other 6 hydrogen, which is like this, you can see this one, you can see like this one, they are equatorial. They are equatorial. If you change the one conformation of cyclohexane into another conformation of cyclohexane, axial hydrogen will be equatorial, equatorial hydrogen will be axial, but the molecule will be same. So one molecule have many conformation. They are the similar molecule, right? But one molecule have only one configuration. If the other molecule have different configuration, it means this is the different molecule. Because if we want to change the configuration of the molecule, we have to break the bond. Just like I've shown you how I change R into S and S into R. Without breaking the bond, we cannot convert the S into R or R into S, right? Means they are different molecule. They are mirror images, but non-superimposable mirror images, they are different compounds. So both enantiomers are 2 different compounds, right? So, and then if the molecule has same many conformation like this, I can move like this, I can move like this, I can move like this, like this, like this. Molecule will be same, because they in the nature the molecule are having the different conformation, because they want to be stay at a low energy, right? So for example, if let's say in the cyclohexane, if like this, you can see in the cyclohexane, I make this cyclohexane in the boat conformation. In the boat conformation, these 2 axial 1,4 diaxial hydrogens are very near to each other. This is called the flag pole interaction. Because of this hydrogen, this boat conformation is in boat conformation is not stable in cyclohexane. Only the chair conformation is stable in case of the cyclohexane, right? So like this, so this is how why the chair conformation is stable in case of the cyclohexane. So now I am replacing, you can see this one chloride, right? So I am replacing this chloride with replacing this one hydrogen with the chloride, this one. You can see this one chloride. I changed this, replace hydrogen with the chloride. That's how you can construct the model, right? And then other chloride, this one, the other chloride, this one. So like this. So this is also on the same equatorial position, right? So equatorial position, right? This one equatorial and one equatorial position, right? This one. Can you able to see this one? This one is chloride and this one is chloride, right? 1,4 disubstituted cyclohexane, right? Like this. Can you able to see?
Yeah.
Yeah, you see this one. So you can see one chloro is at equatorial, other will be the other will be, you can see like this. One will be, you can see one is on the down plane, and other is at the top, right? This is also equatorial, this will also is the equatorial, right? But this is projecting down, this one is projecting up, right? So both have different orientation in a space, right? So they are opposite to each other. So they are trans, right? So how, if I want to convert the trans into cis, I have to break the bond. I have to break the bond like this. So just I am giving you the example how one molecule will have the different orientation, different configuration like this. So you can see without breaking, we cannot convert trans into cis like this, right? They are on the same plane. They are on the same plane, right? So they are cis. But here we are talking about the trans orientation. So we can have the orientation of both chloride is at opposite plane. So you can see opposite plane. This one is at the top. This one is at the bottom. Understand? So how you can form the mirror image of this molecule is very easy, right? It's very easy. Just you can point, you can have this one, right? This one, you have like this, you can see this one. You can see this one, right? So just you have to make the mirror image of this one. So what I can do is I move this one. You can see this one, right? I move this one at like this and this one at the bottom. So this one will be the mirror image of this one. So I can show you in the one of like this, like this. You can see, the mirror images like this one, right? So how this mirror image is, you can see the previous, which I am showing you in the model, right? The model is construct like this, and your answer in the form of the in the form is like this. You have the mirror image, just you have the mirror image like this, right? You have the chloride on the same plane, but they are, you can see, on the equatorial and equatorial. These are the mirror images of this molecule, right? Means, and so like this, so they can be interconvertible. So meaning that if they are interconvertible, means they are same compound. They are same compound but having the different conformation, right? Different conformation. For example, here you can see chloride and hydrogen and hydrogen. Here the chloride is very far away from their hydrogen. So this one is more stable as compared to this one, because in this one there is the opposite charges are attract to each other, right? So mostly the conformation is like this as compared to this one. That's why the molecule was the same molecule have the different conformation. That's how you make the mirror image of the molecule. So you can see, we see the mirror images of this one in the model, right? So in the model you can see this one, how we can convert one molecule into another one, right? So this one is at the pointed one, this one is at the down. This one you can see, this one top and this one is down, right? Like this one like this. Oh, I can show you this one as the very slightly. So you can have the different conformation of the same molecule move up, and this one will be moved down like this. So axial become equatorial and equatorial become axial like this. So this is how it show that so this one you can see in this one like this. This one is the equatorial and axial and equatorial like this. So this the orientation will be the same, right, in the molecule, because the molecule have different conformation, but molecule is same, right? So that's how you can form the mirror image of the molecule. So is the molecule have the molecule A have the this chiral? Yes. Yeah. Molecule A. Yes.
Yeah.
How they are chiral? Yes. So just in the molecule, why the molecule is chiral or achiral? Where this molecule have planar symmetry? Please. Yes, please.
Yes.
No.
No.
Now, just you can come to the one conclusion. Please think. Please, yes, molecule is chiral or not?
The molecule is chiral because the position is different as in transposition.
Yes. Some if the transposition, yes. So these are the trans and cis. Whether these molecules are they have the plane of symmetry or not. On the basis of that one, you can decide whether they are the chiral or not.
It doesn't have the plane of symmetry, therefore it's a chiral carbon composition.
Yes, the object does not have a symmetry, so the chiral will have a chiral.
Yes, right. So so in 1,4 position, if there is any substituent, the cis and trans both have the plane of symmetry, right? So if they have the plane of symmetry, the molecule as whole is not chiral, right? Molecule as whole, the same example which I have tell you in previously, that if the molecule have if the molecule is cis or trans, both isomers are usually have the plane of symmetry. So they can say, you can say that they are the diisomers, right? But they are having they are not chiral. They are not chiral means they have the plane of symmetry, right? So this whether you have the cis or trans, both are achiral because they have the plane of symmetry, right? We have the same example as we have seen previously. So, does a molecule have plane of symmetry? If so, the carbon atom does not. Carbon atom does it go through, right? So, yes, this molecule have the plane of symmetry, right? If there is a plane of symmetry, right? So, if there is a plane of symmetry, so meaning that molecule as whole is a chiral molecule. So, it will not rotate the plane of polarized light. If it not rotate the plane of polarized light, because for the rotation of the plane of polarized light, right, molecule should be chiral, right? So if the molecule having the plane of symmetry, so molecule as whole is a chiral, is optically inactive, right? So if the molecule, so if for in order to be optically active, the molecule should be chiral, right? Molecule should not have the plane of symmetry. If the molecule have the plane of symmetry, then the molecule will be as whole achiral, and it will be optically inactive. The same example you can see here also. This is the cis conformation, right? This is the cis conformation, which is the same as I given you the example. So you see, this one I have shown you. This one is the trans conformation, right? Now I convert the trans into cis. So I have to break the bond and then convert into cis into trans. You can see both chloride is and the same plane. If they are on the same plane, they are called the cis, but they have plane of symmetry, because you have to cut the molecule from various parts. Wherever it can say the plane of symmetry, usually at 1,4 position, whether any subsequence, they have the plane of symmetry. Cis or trans, they are achiral molecule because it has plane of symmetry. Once it has plane of symmetry, they are achiral and they cannot rotate the plane of polarized light, right? So meaning that they are optically inactive. Understand?
Understand.
Right. So now we have the last example, right? So far we have discussed all the possible questions, right? Now we come to the one medicinal chemistry example. This one molecule, application of this stereochemistry in this molecule, right? So this is the molecule which is prostaglandin E1, right? So just you have to apply the previous knowledge which I have given to you, right? This is the prostaglandin, right? Prostaglandin. First of all, that they assign the correct numbering of the compound. So correct numbering of the compound, you have to follow the IOPAC, right? Ruling. So the most in this molecule, which one is the most proteotic group in the molecule? Which one? Can you tell me? From where we can start the numbering, because numbering should be according to the IOPAC, and then we have to select the functional group which is on the top priority. Yes. Yes. Yes.
Is it the one with the oxygen?
Yeah, carboxylic acid, this one. Carboxylic acid, of course, right? Carboxylic acid, ketone, and then aldehyde like this. So this one is the one, number one carbon, number one, number two, number three, number four, number five, number 6, 7, 8, 9, 10. You see, 9, 10. You see the push the 7, 3 hydroxyl group. So like this, so you have this of this 5 oxo group, right? 5 oxo group is this one, right? 5 oxo group, right? So you have the numbering like this. So one here is start from 1E. I was yeah, 1E, and 1E means trans group, right? These are the trans group, right? So the start 1, 2, 3, 4, 5. You have the 1, 2, 3, 4, and 5, and 6 like this, 7, 8. So you have to go like this. One, you have yeah, 1E group, which is the for the double bond, right? And you have the stereochemistry 3S, which is on the hydroxyl group. This 1, 2, 3. This stereochemistry of this group is S, right? 3S, right? And then we have the 3 hydroxyl group. But I have seen this. These are the stereochemistry. Generally, the stereochemistry of this group starts from here. I think this. I'm sure that it starts from here. Yeah. You have to, you can check that whether it's start from here or there, but this is it. I'm sure that start from here. This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Oh, so kindly check this one time, right? But according to me, maybe I am wrong, but it will be start from this carbon. But you can double check this one, right? Thank you. And then how many stereo center in this molecule? The second question, how many stereogenic carbon? Can anybody tell me how many stereogenic center or chiral carbon in this molecule? Yes. How many stereo center?
Is it
Yeah.
3?
No, how? Maybe you are correct, yeah. Maybe. How? Can you tell me?
Because I noticed that the maximum amount of carbon that it states in the definition for any the confirmation, the
Mm-hmm.
I is 3.
1R, 2R, 3R like this, right?
Yeah.
This one. So this one is also a stereo center, right? This one also is stereo center, right? And then this one is also a stereo center, right? Can I? This one, number 3 and number 4. This one also, of course, you can see this hydrogen, oxo group, different group, right? This one group, right? Number 1. Number 2, hydrogen group, hydroxyl group, this group, and CH2. So this one is CH, right? And this one is other group, right? So this is also the stereo center. And then this one is carbon, right? This one carbon, hydrogen group. This one is CHOH group. And then this one is CH group. And this one is CH group with CO and CH2, right? According to this, there can be the 4 stereo center, 3 hydroxyl group. But a stereo center is 1, 2, 3, and 4, like this stereo center. According to the what we have learned, this carbon have stereo center, this carbon is also a stereo center, this carbon is also a stereo center, this carbon is also a stereo center. If you have seen this one, is this one is CO, and then this one is COH, right? So this one have the different groups. This one different group. They have, but if let's say you can see this one CO group and then CO group, then this can be the same stereo center. Then 1, 2 they have stereo center, and 3 can be stereo center, right? 1R, 2R, and 3R group is this one. So R group may be stereochemistry of this one is R, stereochemistry of this one is R, and the other one, this one is R. So according to this, if let's say like this, so 3 center like this, 1, 2, and 3. But according to me, this one is the one stereo center, this is second, this one third, and this one is 4, because this is oxo group here, right? But this is CH2 group, a hydrogen, and this one is also different. So if we assign this one as a CH and this one is also CH, so then they both have the same stereo center, right? So the 1, 2, and 3 can be also correct, but they have the 3 stereo center, right? 1, 2, and 3. So if you assign this maybe CO group and this one is the different group, then only. So, but up to your point, this one stereo center, second stereo center same, right? And then the third one, which is hydroxyl group. This one is. So this is how many stereo center. Does it play a optical rotation? Yes or no? Yes. Does it play the stereo optical activity? Because what is the definition of optical rotation? Yes. What is the definition of optical rotation? Please, I told you.
Is it the rotation of the polarization, rotation of
Yeah,
polarization?
rotation of the plane polarized light. So only if there is a chiral carbon chirality in the molecule, then only the plane of polarized light. It rotates the plane of polarized light, right? If there is a no chirality, then it will not rotate the plane of polarized light. So the molecule have the chiral carbon, of course, right? Molecule have the chiral carbon. A molecule is also not symmetrical. Molecule is also not symmetrical, and it has a chiral. The molecule is not symmetrical, and it has a chiral carbon. It means it rotates the plane of polarized light, right? If it rotates the plane polarized light, then it display the optical rotation. Means it is optically active. Optically active. So yes, so far we have discussed all type of these um examples, right? So in this one, in this molecule, you have the stereochemistry of this molecule. Just hold on. Can share this one. Why this always no not share? Hmm. So in this, so can you able to see this one, right? So in this molecule, right? So just you can double check this numbering. In my point of view, that maybe numbering start from one from here, right? 1, 2, 3, 4, 5, 6, and so on from here to here, right? But according to their IOPAC, you have to just check the numbering of this compound, right? And the second is how many stereogenic center or stereogenic carbon, right? So we have seen the one stereogenic carbon, and second one this one, and third three stereogenic carbon, right? And if there is no plane of symmetry, then it display the optical rotation. Yes, it has a chiral carbon, right? It has the stereogenic center, and it rotates the plane of polarized light because molecule has the chiral carbon and it has no symmetry, right? So if there is no plane of symmetry and chiral molecule is having chiral carbons, right? So as whole molecule you have the chirality. It rotates the plane of polarized light. So like this. So we have gone through with all the examples. So we have construct the molecule alkane and cycloalkane, right? And we have seen the different isomers of these 2-chlorobutane R and S. We assign the stereochemistry of the through the model, right? Through the CIP rule, right? In this, you have to just give the priority to the largest group and then hydrogen at the back, right? And then you can root weather molecule, and then you can see A, B, and C higher to the lower, right? And if the molecule is can rotate and see the priority level from higher to lower. If clockwise rotation, then it will be R. If anti-clockwise or counterclock, then it will be the S. Then we have construct the molecule 3D and convert that 3D to this Newman projection. So one molecule have different conformation, whether Newman projection or different new projection, Newman or Sawhorse projection or the Fisher projection. These are the different projections of the same molecule. Understand? These are the different projection of the same molecule. If you want to convert one molecule into another one or one enantiomer into another, you have to break the bond like this. So like this, we have break the bond. We substitute hydrogen with the chloride, substitute the chloride, they substitute Ha with the chloride, Hb with the chloride, and see whether they have the same molecule or different molecule. Of course, they are not identical molecules. So whether they are enantiomers or disomers, you have to decide, and then you have to assign on the base of the CIP how whether these models are R or S. So you have to rotate whether this C2 carbon is R or C3 carbon is the S or R or S or S or R or S or S, like this, right? So the same thing we have done with the other isomer, right? This S isomer of 2-chlorobutane, we have replaced the Ha with the chloro group and Hb with the chloro group, and we have seen whether they are similar or not. So like this, so with the help of this your previous answer, you have to see uh, um, check whether molecules are identical or enantiomers or isomers. If the molecule have the plane of symmetry, or if the molecule is similar can superimpose, they are identical molecule, right? And if the molecules are non-superimposable mirror images, they are enantiomers. And if they are not mirror image to each other, but they are chiral, so they are distereoisomer. If the molecule have plane of symmetry, which I have told you, if the molecule have two similar groups and two dissimilar groups, right? So the molecule have the plane of symmetry. So the molecule is having the plane of symmetry, they are called the meso compound. They are the meso. They have the plane of symmetry. So plane of symmetry, so it doesn't mean if for example one molecule have two chiral carbons, but they are similar, they have the plane of symmetry, then the molecule as whole called the meso molecule, because they a molecule has a plane of symmetry. We have seen the example of cyclopentane, and we have removed one hydrogen, exchanged one hydrogen with the chloride, and the same we have seen the dichloro and the cis and trans. But if the molecule is cis, then you have to see whether it is cis molecule have plane of symmetry or not, and the trans molecule have same plane symmetry of or not, like this, right? So you have to assign the stereochemistry of these carbon also, right? And then we have seen the example of cyclohexane, 1,4-dichloro. So we have I've shown you the stereochemistry, the mirror image, how you have to form the mirror image, right? So whether if the molecule is cis or trans, in both conditions, they have the plane of symmetry. So molecule as whole achiral, it cannot rotate the plane of polarized light, because if molecule is plane have the plane of symmetry, so molecule does not rotate the plane of polarized light, right? The same you have to see, you have to just make the mirror image of this molecule also, right? The same as I have shown you the in case right, like this. And this one is for the trans one, right? So in the trans one di substituted, you have like this trans. This is the mirror image of the this trans 1,4 di substituted chlorocyclo 1,4 dichlorocyclohexane, like this. So this I have shown you. This one you can see they have the plane of symmetry. If uh, uh, molecule A is chiral, of course, no molecule A is not a chiral because it has a plane of symmetry, right? So it cannot rotate the plane of polarized light, right? So it's because it has a plane of symmetry. The same molecule molecule B also is no chiral because it has a plane of symmetry, yes, and then it cannot rotate the plane of polarized light, right? So we have seen these examples that how these molecule have the plane of symmetry. You can put the plane and it is just a symmetrical molecule both sides, right? So this is how the other example, how you convert the Newman projection into Sawhorse and 3D. We have seen the example of this molecule. Understand? So yes, hello, yes.
Understand.
Yeah, so I have gone through
Yes.
most of the examples, I think most, right? So I think yes, just only left. I'm but bit confused with this example of the numbering of this compound, right? only the numbering of this compound, because what I have seen in the literature started from here. But please check please one more time, you can check the numbering of this compound, which is the prostaglandin E. But for the stereochemistry is it has three stereo center, right? If let's say if CO, this one is carbonyl CO, but it is also considered as CO. So according to like the CO and CO, these two hydrogens have the same chirality. So one stereogenic center, two stereogenic center, and three stereogenic center. But if let's say someone can put this one as one stereo center, that also will be okay, because this is all logically, this will be R, this will be R, this will be R, and this will be R or S, right? So this is how. So that's why you can see this one, this 3S, 1R, 2R, and 3R. This one is 3S. So according to this one is 3S because of this one. 1R, R is 1R, 2R, and 3R, right? So this one is all R, and this one is the S stereochemistry. So according to me, this is can be some can answer this 4 and some can 3. But according to this, if this one is also stereo center, this also stereo center, this also stereo center, this one is 4, is absolutely, I think so, the correct answer, right? And then this molecule has no plane of symmetry, it's non-identical molecule, and it has chiral carbon, right? So it can rotate the plane of polarized light. The molecule is optically active, right? So you have to answer this all, right? Answer these all the questions, right? I think this I'm able to um, convey the most of the discussion according to related to the stereochemistry, right? So how to make the model, and then from the model how you can construct the Newman projection, and how you study the Newman projection uh, Newman projection in order to assign the stereochemistry of the chiral carbon. We have seen the model, different models. It started from 2-chlorobutane, and then we have different isomers, and then we convert 2-chlorobutane into 2,3-dichlorobutane, and then after this stereochemistry of both carbons, and then we have seen some of the example of the cyclopentane, and then replacing the second hydrogen with the chloride group, right? And then we have seen the example of cis and trans 1,4-dichlorocyclohexane, right? So in this cis and trans we have seen, and we have found that there's a molecule having the plane of symmetry. If the molecule has having the plane of symmetry, it means the both side have the same parts of the structure, right? If have the plane of symmetry, if the molecule having the plane of symmetry, it means the molecule as whole, although it have molecule as having the chiral carbon or not, but molecule as whole is the achiral. If the molecule as whole achiral, right, achiral because of this plane of symmetry, then it cannot rotate the plane of polarized light. So if not rotate the plane of polarized light, the molecule as whole is optically inactive, right? So far I'm able to convey the most of the part of your practical. So if you have any question, you may ask. Thank you. Students, yes?
Can I ask something? Is this practical a group one or an individual one?
That you have to ask with the Dr. Sadia. I don't know exactly, right? But you can ask with your class rep to contact to Dr. Sadia, right? So I hope so. I don't know exactly. Really, truly speaking, I don't know whether it is a group or it is individual, right? You may ask, you may request to your course representative to confirm, double check with Dr. Sadia, right? Right. But the meaning is that you all have to be should have the clear concept about the stereochemistry, how we can make the 3D model. Although you don't have the 3D model, but it's easy that you have the carbon, hydrogen, chloride, but through the 3D model, you can able to understand the stereochemistry in a very good manner, because from this one you are able to know that how the molecule the molecule shape in the space, right? How the and then the molecule is the single bond free rotation. If they are the free rotation, then it can have the different conformation like this, like this, like this, like this, right? So once the molecule have the different configuration, means I break this hand and then substitute with the this this with the leg, right? So meaning that there's a different configuration, right? So now these one also are not same. So right, if you convert into one molecule into different, we have to break the bond. So mean break the bond, we change the configuration of the molecule. But one molecule can have different conformation, but molecule will be the same. So you should have to have the different clear concept about the stereochemistry. This is my aim, right? The lab regarding the lab report, you can ask Dr. Sadia that whether you have to submit in a group or individual. Yes. Anyone else?
No, doctor.
No questions?
No.
Okay. So far, so you are so far you have able to understand.
Yes.
So yes, so hopefully from online is through the models. I think yeah, if let's say you are in front of the model, then it will be more you can understand in the in a good manner, right? But I hope I am able to convey all this the concept of the stereochemistry and enantiomer, diisomer, meso, and identical compounds, right? So far, if you have no questions, right? So thank you very much for for attending this practical, right? So hopefully you have all uh, put your attendance right with your yes group E, group F, and group E, right? So if you have no question, uh, uh, then it's okay, right? So later you can ask if let's say you have any confusion, right? So inshallah, till then, inshallah, assalamu alaikum. Okay. So
A
I'm
question
yeah,
regarding
yeah,
the
Ken.
recording for the session. Will it be posted in Google Classroom, or do I have to email you personally for it?
No, I will try to post it by as I will ask the course coordinator, right, the RP, and then I will post, no problem, right? Inshallah, you will get the video, no problem, right? So by this afternoon or this evening, you will get the posted on GC, hopefully, inshallah, right?
All right.
Okay, thank you very much. So I'm just leaving this session, right? Thank you very much. Assalamu alaikum.
Thank you, Doctor.
Thank you,
Waalaikumsalam.
Doctor.
Thank
Thank
you.
you,
Thank you,
Doctor.
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 Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.